If you notice, I put this in vascular for reasons, but this is today's asynchronous assignment. Oh, maybe I shouldn't have this in vascular. Well, in any case, doesn't matter where the Zoom came from. I'll decide where to put this later. But just forgot we didn't have class today, so I will not see you live in person until the end of the semester, until after the end of the semester. So today I just go through some questions, some wordy questions, which are good because they throw a lot of curveballs at you. And so that'll be it for today. So let me pause recording here. And starting with 249, excuse me, on page 475. Nice wordy question. Let's see. An acoustic wave in medium B. Right off the bat, they're kind of getting you with, why would you start with B? Doesn't everyone start with A and go to B? But no, they go from B to A. Well, that's part of the reason I wrote this one down. That just a very small wrench they threw at you, a little confusing. Not very confusing, but just enough to tip you if you're not paying attention. So acoustic wave in medium B is traveling towards medium A. And the sound beam strikes the boundary at a 45-degree angle. The propagation speed is 1547 for A. So we gotta keep this in. So the second medium is 1547, and the first medium, 1745, is for B. Let's write that down. First, second, because if you don't write that down, or if you don't keep that straight in your head, you will get this question wrong, even though you know how to do it. What is the angle of transmission? Okay, it starts out at 45. We're not going to know what the real angle is. That's another reason why I crossed out the true here, because it's the true angle. That kind of makes it sound like you have a real number to go to. Well, we don't. And you can see that in the answers. The answer is greater, less than, equal to, cannot be determined. We should be able to determine this. There's a speed change, therefore refraction should occur, right? And the first is faster than the second. It slows down. So we should be talking about less than 45, which is yes. Letter B is the correct answer. And how do I do less than? Yeah. Do that a little cleaner. There we go. Less than 45. It slowed down from 1745 to 1547. Great example of a question that I probably would get wrong, because I read these just like you guys do, a little too fast sometimes, and I think I know the answer so quickly because I'm so smart, and then I get things so wrong because I'm not paying attention. And just like you, 251, looks like I abbreviated this. I didn't feel like writing it all out. I'll read from the book. A wave of acoustic energy is leaving soft tissue and transmitting into fat. Okay. Remember what we said about fat. Fat is slow. Let's just write that off in the corner. The tissue and transmitting the fat with an 86-degree incident angle. Before, on the previous one, the beam strikes the boundary at a 45-degree angle. This one, the beam is incident upon the boundary at 86-degree angle. same words, different number, but same words, or the same meaning. What is the true angle of transmission? So I already scratched out true in my on this. But let's see, we went from fast to slow, right? Wait a minute. Yeah, I went from fast to slow. That should be slow down. And yes, the answer is once again B, less than 86 degrees, because it's slowed down again. Okay, 255. I skipped a couple because it's probably just repetitive. 255. What do we have here? Time of flight. In soft tissue, sound travels to reflector and back to transducer in 39 microseconds. How deep is a reflector? How deep is that reflector? Okay. Well, we know, of course, about the 13 microsecond rule. Or here, let's just erase rule and just say equals 1 centimeter. Plus 13. Let's know. Why draw it in such a confusing way? All right. Plus 13 microseconds. That's another centimeter. Well, we'll do that. That's another 1 centimeter. And then plus 13 microseconds is 1 centimeter. 13 plus 13 plus 13 is actually 3. 3 plus 3 plus 3 is 9. 39 microseconds. 1, 2, 3. I know that one's probably pretty obvious. The other thing, guys, is if you forgot the 13 microsecond rule and for some crazy reason you actually remember the depth in meters is equal to speed of sound times time divided by 2, because it's a two-way. I just answered the next question. But anyway, and if you put 39 into the question here, 4 and 2, and you work that all out, you would actually get 30 millimeters, which is 3 centimeters. I know I drew that all kind of small, but I doubt that's the way you're going to figure this question out, by actually doing the entire range equation. But you could throw 39 into the range equation and see that you come up with 3 centimeters. Remember, 13 microseconds is just the easy, I'm sorry, I'm filling my pond and I see that it's overflowing. I'll be right back. Okay, disaster averted. 2 major reasons you don't want to overfill a pond with fish with tap water. One major reason, especially in this town, we have a lot of chlorine in our drinking water or tap water, and chlorine is not good for fish gills. They can't breathe. Little fun fact, I believe what it does is it takes the space in the gill that normally would be for gas exchange. It kind of gets stuck in there. But then the other issue is that overflowing water really messes with my subduction of the ground around there. Anyway, fun. What is the total distance traveled for sound in the previous question? What is the total distance traveled for sound? Three centimeters might be the depth of the reflector, but the sound went there and back. So 6 centimeters is how far it actually traveled. That was 256. Soft tissue. Yeah. Okay. Let's see. 260. I jumped to page 477. What do we have with this one? Oh, yeah. All right. The axial resolution of an imaging system is reported to be 0.85 millimeters, 0.85 millimeters at the focus. What is the closest estimate of the system's radial resolution at a location that is 5 centimeters deeper than the focus? What? That's the problem with, well, it's not just ultrasound. A lot of things in life. Different words will mean the same thing. Lard, longitudinal, axial, range, depth. Whoops, range, radial, and depth. Those all mean the same thing. Longitudinal, axial. We always use the word axial resolution. But you could say longitudinal resolution, range resolution. And I really don't like the word range resolution because that seems like it's talking about how good it is at the 13 microsecond rule. But unfortunately, it's there, axial, range, radial, and depth. Now we come back to this question and we realize it's simply asking the axial resolution and axial resolution again. That is tricky, unnecessarily tricky as far as I'm concerned. They should just, all these eggheads should get together and agree on one word. But in any case, the meat of the question, I mean, that's just a trick. Then there's the meat of the question. The imaging system is reported to be 0.85 at the focus. What is it at 5 centimeters deeper? 5 centimeters deeper. Ha. Okay. You guys know you're not going to be asked to do a whole lot of math on the SPI. And you should remember that axial resolution not change. So it's the same. It's, let's see, equal to. So letter B, equal to. If it's 0.85 at the face, it'll be 0.85 at the focus. It'll be 0.85 at 2 near zone lengths. And why is that, guys? Because axial resolution is the number of cycles that will not change, and wavelength. Okay. Of course, we do have to assume, we have to make some assumptions here, but under all those assumptions, like speed of sound doesn't change through tissues and all that, the wavelength will not change either. So axial resolution does not change. It actually does change depending on the speed of sound, but we're not talking about that. Okay. System A. Ooh, this one. Now let me read from the book because I whoops, didn't read. I didn't write down everything. 261. Two systems are undergoing evaluation. System A has 1 million pixels, each with 4 bits. System B has 750,000 pixels, each with 12 bits. Which system has the best longitudinal resolution? Best longitudinal resolution. Pixels and pixels and. Well, wait a minute. What's longitudinal resolution? Longitudinal, axial. It's axial resolution. Now, this is an easier question to answer. We don't know. This information doesn't tell us anything about axial resolution. Axial resolution, of course, is number of cycles and wavelength. 262, I didn't write it out, true or false. The lower the numerical value of longitudinal, once again, axial, the lower the numerical value of longitudinal resolution, the worse the picture. False. Smaller or shorter is better. It's like playing golf. You want your score to be small. At least I think that's how golf is played. Okay. Oh, I have a little swig of my wonderful coffee. 266. I'll read from the book. An ultrasonic pulse has a pulse repetition period of 1.2 milliseconds, a spatial pulse length of 2 millimeters, and a wavelength of 0.4 millimeters. What is the axial resolution of the system? What did we just say? Does pulse repetition period have anything to do with it? No. Does spatial pulse length have something to do with it? Oh, yeah. And a wavelength of 0.4. Wavelength has something to do with it. But at this point, I'll do a funny underline. We don't need it because we have all we need right here. The spatial pulse length. What is the axial resolution? 266. It better be letter B. Yes, letter B. Oh, right, of course. Axial resolution is equal to 1/2 the spatial pulse length, or another way of writing that is simply the spatial pulse length divided by 2. 2 divided by 2 is 1. Capiche? Makes sense? We could find out how many cycles there are by looking at the wavelength and knowing that the product is 2. So 2.0 is equal to X number of, actually N number of waves times 0.4. I guess, anyway. 267 I didn't write out, but let's look at that. 267. True or false? The more cycles there are in a pulse, the greater the detail that will be visualized in the ultrasound scan. Doesn't that sound so true? Doesn't that sound true? False. The more cycles in a pulse, the greater the detail that will be visualized in the ultrasound scan. What are they asking? The greater the detail. They're asking about axial resolution. Is this pulse going to give us good axial resolution? Half the spatial pulse length is this long. Longer is not better. Shorter is better. So this is actually a false statement, even though at first glance it would be, yeah, that seems right. 268. Okay, I didn't write this one down at all. I got lazy. So read along, or I'll just read it to you. Right, okay. Two ultrasound systems produce acoustic pulses. Well, no kidding. A pulse from system 1 has a wavelength of 0.5 millimeters and 4 cycles per pulse. Let's go ahead and write that. Because basically they just gave us the needed numbers for spatial pulse length. Let's go ahead and just write spatial pulse length. And I'm going to write it cycles first, because that's how we normally write this. 4, n equals 4 cycles, and let's just write cycles, times a wavelength of 0.5 millimeters. So that was basically n times wavelength. This is number 1. Spatial pulse length 2 is equal, as far as a pulse repetition of, and a PRP. Oh, okay, well, here's the first hint. I don't think, going through this question, I don't think we're going to need the PRP. The pulses from system 2 have a wavelength of 1 millimeter and 2 cycles. So 2 cycles times 1.0 millimeters. This is starting to look good. Let's see. And a pulse repetition of 1.8. Which ultrasound system will have the lower numerical value of axial resolution? Okay. PRP has nothing to do with it. So those numbers truly are not it. Let's see. 2 times, let's just make it 10. Let's just say 2 times 10 is 20, but it's actually 2.1. So this one is 2.0 millimeters is, oh wait, that's axial the spatial pulse length. Yeah, right. I'm just seeing what the answer is, because I want to see what they're getting to, because we're actually asking about axial resolution, not spatial pulse length. But of course, 4 times 5 is 20, but this is 0.5, so that's actually also 2.0. So very different wavelength. So probably very different frequencies. But this transducer is better built. It only has 2 cycles, whereas this one up top has 4 cycles. So they end out, even though they have different frequencies, they end out having the same spatial pulse length. Now, in the real world, that probably doesn't happen like that, but certainly not with the same manufacturer. Okay, and so, and by the way, axial resolution for both of these is 2 divided by 2, right? 2 divided by 2 is 1 millimeter. Both of them are 1 millimeter. So it's, in other words, the same. And then I think we end on 269. No, we end on 272 because it was a mean one. 269. Best axial resolution. Which one has the best axial resolution? Well, we just kind of worked it out a little bit, right? But first thing I'm looking for when I do this question is I make sure that these are all the same. They're not sneaking a kilohertz in there, right? Because that would totally change the question or the answers possibly. Okay, so they're all megahertz. Yep. And we have a high frequency. But what does that mean for us? In other words, this is half the wavelength, right? Should be half. Well, in any case, we don't have to go this far. I mean, I guess, because I just quickly looked at the answer. We can go and figure out what the wavelength is for each of these. And then we'll just call this a full wavelength here, full wavelength, half wavelength. But that doesn't really matter. All that matters is higher frequencies, better axial resolution, smaller wavelengths, better axial resolution. So better. So let's see. We like that. We like that. Let's go to blue color. And best axial resolution, fewer cycles. We like that. And we like that. Oh, dear God, what did I do? Oh, I just looked at the answer for 270, which is the exact opposite question, and I pooped myself. Okay, yes, it is letter A. We just checked the best and the best. This was unnecessary stuff over here. I guess I kind of went a little bit overboard. Yeah, and by the way, so 279, the which is the worst. Worst, and well, that one's worse, but this is worse and worse. So C for 270. Okay, this last one, I'll let you go, but hang on, hold on to your hats. This one's a doozy. Totally, if it weren't for the answers making me rethink what the heck I was looking at, if they gave, oh, I could imagine some other incorrect answers that I definitely would have gone for. So this is a mean question. Let me read from the book. I think 272. A sonographer is performing a study on a patient and desires superior depth resolution. Which of the following changes would create such a system? And of course, my thought is depth. I want superior depth. Lower frequency, longer wavelength, you know, what else? You know, that's exactly where my brain was going. Because I forgot and wasn't paying attention. The sonographer didn't want superior depth. They wanted superior depth resolution. He wants, I keep saying he, they, axial. They want axial resolution to improve. Okay. Well, after a chapter or two of him saying you can't change it, now he's giving you a question where apparently damn it, they are changing it. Higher frequency, better axial resolution. Shorter wavelength, yes, better axial resolution. Fewer cycles, better. Less ringing, same thing as fewer cycles, yes. All of the above is correct. That is a mean question because I had to read the answer all the way through going, I don't understand. And then finally it struck me, I'm like, depth resolution, axial resolution, that's what they're asking for. Oh, well. But if you take your time, read the question, look at the answers. If something doesn't feel right, look at that question again. And very often, at least for me, very often, I realize I missed a key word, and my eyes just went right over it, thinking I knew what I was reading. So that's why I kept this one in here. All right, that is your asynchronous assignment for Thursday, Friday. I guess by that definition, it has to go into lab, but we've got, I don't know. All right, I'm going to stop talking now and talk to you all later.